Ever wondered how your bike knows when to stop, or how a cricket ball magically reaches the boundary? It's not magic, it's physics. Today, we're unlocking the 3 secret formulas of motion that can literally predict the future. Okay, not your exam result grinning face with sweat, but definitely motion. So today, we're diving into first equation of motion, second equation, third equation, and a sneak peek into circular motion and angular velocity. Okay, imagine this. Your car is moving from point A with increase in speed till it reaches point B. Point A is where you started, so your initial velocity equals to U. Point B is where you reached, so your final velocity equals to V. There is a line going up. That's your speed increasing to reach point B. And the time taken to reach point B from point A is t. From the graph we can conclude, AB is a slope, which is acceleration denoted as A of the car. AO or DC equals to initial velocity denoted as U. BC equals to final velocity denoted as V. OC or AD equals to time denoted as t. Now here's the fun part. The object is in uniform acceleration. I'm sure you have seen module in which I explained acceleration of the objects. If not, click the link in description. Now, acceleration is defined as change in velocity divided by time. From the above, acceleration is AB. Change in velocity is BD. And time is OC. Substituting these annotations we get, AB equals to BD upon OC. We also know change in velocity is BC minus DC, hence BD is replaced by BC minus DC. Putting the values of these annotations, we get A equals to V minus U upon time. Now just rearrange it. And boom, we get our superstar, first equation of motion, T plus U equals V. This equation tells you, the longer you accelerate, the faster you go. So now that we've mastered the first equation, let's level up. What if I ask you, how much distance did the object actually travel? Again, we take the same situation, but here's the game-changing concept. Distance traveled equals area under the velocity time graph. The shape under the slope is a combination of a rectangle and a triangle. So total distance OABC equals area of rectangle OADC plus area of triangle ABD. Substitute the formula of rectangle and triangle. Area of rectangle is length multiplied breadth. Area of right angle triangle is half multiplied base multiplied height. Now, use annotations using the graph. Length of rectangle is OC, breadth of rectangle is AO. Base of triangle is AD. Height of triangle is BD. Now, replace these annotations with values, OC with time t, AO with initial velocity U, AD with time t, BC with change in velocity V minus U. Using acceleration formula, V minus U equals to AT. And, hooray! We get our second equation of motion. Okay, quick question. What if in a numerical, time is not given? Don't worry, because this equation is your ultimate backup plan. Let's take our favorite velocity time graph again. Object starts with initial velocity U, reaches final velocity V in time t. Note, acceleration is uniform. Now look carefully, the area under this graph forms a trapezium. Distance traveled equals area under velocity time graph, which is area of a trapezium OABC. Formula for area of trapezium is area equals half multiplied sum of parallel sides multiplied by height. Area of trapezium equals to displacement of the car, which is denoted as S. Substituting annotations from the graph, we get S equals to half AO plus BC multiplied by OC. AO is initial velocity U, BC is final velocity V, and OC is time t. Since time is not given to us in this scenarios, so we can derive the value of time from acceleration formula or first equation of motion. Time equals to V minus U upon it. Replace t with this in area of trapezium formula, we get our third equation of motion. Remember, the final step requires identity third from algebra, which is a square minus b square equals to a plus b, a minus b.
An airplane accelerates down a runway at 3.2 meters per second square for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. Let's note down the given values. Acceleration equals 3.2 meter per second squared. Time t equals 32.8 seconds. Initial velocity u equals 0 meter per second since the airplane starts from rest. To find distance, we use the second equation of motion, s equals ut plus half a t squared. Now substitute the values into the formula. S equals 0 multiply 32.8 plus 1 by 2 multiply 3.20 multiply 32.8 squared. So, the total distance traveled by the airplane before takeoff is 1,721.34 meters. Here is a practice numerical for you to solve. Pause this video, solve this numerical and tally your answers shown here. Did you ever wonder why Earth takes exactly 365 days to complete one revolution? Or why satellites and the moon don't fall down to Earth? These questions might seem different, but they are actually connected by one important concept in physics: uniform circular motion. Uniform circular motion is when an object moves in a circular path at a constant speed. In such motion, the path followed by the object is called an orbit. Even though the speed remains constant, the direction keeps changing, which means the object is continuously accelerating. The displacement in circular motion is called angular displacement, and the velocity is known as angular velocity. The acceleration acting on the object is called angular acceleration. That's why circular motion is also called uniformly accelerated motion. To calculate speed in circular motion, we use speed equals distance divided by time. Since the object moves in a circle, the distance becomes the circumference. So, speed becomes 2 pi r divided by time, where r is the radius of the circular path. Let's solve a real-life example. An artificial satellite is moving in a circular orbit of radius 42,250 kilometers. Calculated speed if it takes 24 hours to revolve around the Earth. Using the formula, speed equals 2 multiply 3.14 multiply 42,250 divided by 24. Solving this, we get speed equals 11,055.4 kilometers per hour. So, the satellite moves at a speed of over 11,000 kilometers per hour to stay in orbit around Earth. And with this, we have successfully completed Chapter Motion, Module 5. Now you have a strong understanding of how objects move, from straight line motion to circular motion. Up next, we'll dive into an exciting new chapter: force and laws of motion. So make sure to like, comment, and subscribe to the channel, and stay tuned for more easy and interesting physics tutorials.